Hello everyone, I'm Yuan, and today I'm going to share our work Hello, a heterogeneous logical optimization framework by hierarchical clustering and graph learning. And this paper is co-authored by Yuan, Fanzhou, Zhuolun, Keren, Ronglian, Ziyi, Zongyi, and Bei. Okay, so let's start the presentation. First, let me introduce the concept of logic synthesis flow. So we'll know the logic synthesis just starts from the RTL design, which is the high-level design the abstraction modeling the digital circuits, and then it is converted into the Boolean network. On the Boolean network, some logic-independent optimization will be conducted, and then the technology mapping is conducted to get the gate level net list. Okay, so we know that Boolean network is usually represented by DAG, and there are several DAG types for a Boolean network, including AIG, MIG, and something. Mm, and for the logic independent logic optimization, the main purpose is to manage the node count and the depths. There are several optimization strategies such as rewrite, rebalance, and so on. And there is the trade-off for the node count and depth. So usually people will optimize the node depth product, NDP for short. Okay, and then let me introduce one rising trend for logical optimization, which is heterogeneous logical optimization. So its main idea is to represent different circuit portions of the circuit by different deck types and optimize these portions separately. And the motivation is that like different deck types just demonstrate different expressive power for specific structures or functionalities, and it leads to different logic optimization results. Okay, so one example is that the MIG's type is effectively represents the carry operators, and so it's leading to better optimization results compared with other representations. Okay, so there are several previous work for heterogeneous logical optimization, for example, mixing and the LS Oracle. But for mixing, like it's just to detect some specific components such as AND, OR, and XOR in a circuit and render the optimization separately. But its drawback is it is hard to extend to other gate types. And for the LS Oracle, it includes three steps. First, it's just render the main card circuit partition, to partition the whole circuit into sub-circuits. And second is that it conducts a CNN to predict the best fit stack type for each sub-circuit. And during the prediction, it's just treat the circuit as an image. And the last step is to render logic optimization for each subcircuit based on the predicted deck type. Okay, so there are two main limitations of LS Oracle. The first is that um, during partition, like some sub-circuit portions may consist of logic components with varying structures and functions, which is hard to determine the unique best fit deck type for each portion. And second is that during the best fit tag type prediction, it's just to treat the task as image classification, which lacks the utilization of topological information. Okay, so there are two motivations we observed for the heterogeneous optimization. First is that when two subcircuits demonstrate similarities in their structures or functionalities, they often select the same deck type for the optimal optimization results. The reason is quite intuitive because, like, the efficacy of different deck types varies with different Boolean functions and the topological structures. And circuits with similar functions or topologies, we think they may choose the same deck type to maximize the expressive power and optimization outcomes. Second observation is that if two interconnected subcircuits they are functionally or structurally similar, then merging them into a single circuit will lead to better optimization result compared with optimizing them separately. The reason is that uh, existing multi-level optimization algorithms are code-based, and if you merge the two subcircuits, like new code choices will be generated, and the solution space will be enlarged. Okay, so right now let me introduce our proposed algorithm. First is the overall flow. So given the whole logic network, we will first do the initial clusters generation, and we get some clusters here, and then we do the bottom-up clustering to form the subcircuits across like step by step, and during which we will use the GNN model to generate the DAG OPT embedding, which is used during the clustering step. And we can see after the clustering step, like circuits are partitioned into several subcircuits, and then we just again use the GN model to predict the best feedback type for each subcircuit, and then we we represent them to by the corresponding deck type and optimize them with the corresponding algorithms. Okay, finally, we just convert them all into a unique representation and render the heterogeneous logic optimization to get the final optimized logic network. Um, so here our method just overcomes the two limitations of LS Oracle. First, the limitation is that the partition may consist of logic components with different structures and functions, so it's hard to determine the best fit deck type, right? So our solution is agglomerative clustering. That means we just generate the subcircuits from bottom to up with the unique element as the initial cluster, right? And so for one initial cluster, it's treated as like have the unique or have the complete functionality and structure. So when you use them at the elementary unit, you will guarantee that the subcircuits you generated will opt to have the unique best fit depth type. And second is like the drawback is like the best fit deck type prediction is treated as the image classification task. So here we just use GNN, a customized GNN for the prediction task. Okay, so for the ZAG OPT embedding space, the purpose is to quantify the structure and the functional similarities across various circuits, which are used for agglomerative clustering. So here, the method we constructed the embedding is like we represent one circuit into the four deck types, and we render the logical optimization on them to obtain the NDP, and we compile the NDP values into a 4-bit vector like these. The sum of the vector equals to 1. So this is the DAG-OPT embedding, and we see that if two subcircuits are similar in functions or the structures, they will share the similar DAG-OPT embedding. Second is our customized GM model. So it consists of two modules. The first module is GIN, which is good at like capturing the local structural information. And second is TGNN. It just follows the topological order message passing scheme, which mimics the logical simulation process, and it's good to capture the global and structural information of the circuit. This is the agglomerative clustering steps. The first is that we generate the initial cluster, treat the fine cone of each PO as each initial cluster, and then we use the GNN to generate the DAG OPT embedding, and then we merge the two clusters with the most similar embedding to a circuit. And the Step 3 is repeated until some termination condition is achieved. The reason for choosing the PO fan income as initial cluster is like it will preserve the complete structural information and preserve the independent functional information. Okay, this is a visualization of the Jacobian, like the agglomerative clustering. Okay, so for the hetero logical optimization, we just first use the GNN to generate the Jacobian embedding. And then the deck type or the deck beat corresponding to the smallest value is chosen as the best fit deck type, and we just represent the subcircuit into this deck type and optimize it using the script provided by LS Oracle. And finally, we can convert all the circuits into the MIG representation with no change of node count and depths. Finally, we'll do a global rewrite to get the final result. And this is the experimental part. First, for the data set preparation, we just prepared around like over 5,000 subcircuits for training and testing. And we used the LS Oracle script to obtain the Dagobit embedding for these subcircuit at the ground truth for GN training. And this is the distribution of the subcircuits favoring different deck types as the best fit deck type. Okay, so the prediction accuracy of the trained GNN is like around 80%. And for the heterogeneous stack optimization result, we just choose ABC, Flowtune, MockTurtle, and LS Oracle as baselines. And we compare the technology independent logical optimization and the technology mapping, use ASAP7 PDK node. Here is the technology independent logical optimization result. We can see that compared with all baselines, the NDP of our proposed Hello is improved. And also for the technology mapping result, we also get prominent improvement on the aerial delay product metric. This is the runtime analysis. ABC is very fast, but it's less effective in optimization. Flowtune conducts the multi-arm band exploration, so it's slower than ABC, and MockTurtle is slow for optimizing the whole large Boolean network. As Oracle is slow because it has to enumerate each deck type optimization for each subcircuit. Okay, as that's the end of the presentation. Thank you very much.